Hi, hello.
Yes, ma'am. Yes, ma'am.
Yeah, actually, my system got into recovery mode and the recording was cancelled. Take other. After questions, you can leave. I'll teach some of the things. So it's okay. We have to see. Hello, 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 hello. My mic is
Yes,
working.
ma'am. Yes.
You please say one
Yes.
thing. Yeah, yeah. This one is also working. So okay, we'll start with questions, and whatever we have discussed is not recorded till now, but it's okay. Like we have not discussed much about the things. So okay, then we can start the session. Um, Welcome to this eighth session, week live session, and today we only have questions on the call, and so we are discussing with the questions. Earlier we had some discussions related to mixer and modulation, not much, so we can actually start with this questions and all. So question number one. Consider a message signal MT sampled with frequency Fs greater than the Nyquist rate Fs, which is 2 Fs is equals to 2 FM. The original signal can be reconstructed from the samples M by Fs as. So since you are with me, question, let's solve this question. Like I wanted that you please solve, and then we'll I also solve.
Okay, ma'am.
Hello, are you solving?
Yes, ma'am. I'm solving it. Ma'am, I think answer will be A. First one.
Okay. So,
FSP. Yes, ma'am.
how you have solved?
Ma'am, in the frequency domain, we will use a simple rectangular pulse, and if we convert that rectangular pulse centered around this sampling frequency into time domain, then we will get this expression of sync, and we are multiplying it by the message signal.
So, actually, this Nyquist, I'll use different color. Nyquist rate is nothing but 2 into FM, and you know this after sampling, you have this one. This one is MSF, which is F, and 0 Fs, 2 Fs, and this will carry on till minus Fs and minus 2 Fs. And so what we are trying to do is actually we want this M n by Fs. Okay, so we will pass it to a filter, and we need this type of expression. So you know this one is minus infinity to infinity. What was the expression for that? M
NTS.
NTS sync
FS.
FS T minus NTS.
NT.
Yeah,
Yes, ma'am.
this was our expression for the filter. Now, what we are trying to do, Fs. Now the expressions are given in the form of Fs. Okay, so Ts is equals to 1 by Fs. Now the expression should be for this HF. This one F. This one is HF. And this one HF. And equals to minus infinity to infinity M n by Fs sync Fs. Sorry, this one is Fs only. T minus n 1 by Fs. Just let me know if I am wrong anywhere. So you have tell the answer is okay. Nice.
A.
Answer is A. I'll request the viewers, if you have any queries, you can just mail me in ee21resch 01010 at, at the rate iith.ac.in, because sorry, the earlier sessions were not recorded due to some my window issue. the system went into window recovery period. So I want to say I want to apologize for that. So you please see. So a uniform quantizer with an odd number of quantization level is odd number of quantization level. Mm,
Yes, ma'am. It will be mid-trade.
mid rise na mid trade or mid
No,
rise.
ma'am. Mid-trade, not rise.
Mid
Rise will
trade.
be when there is even number of quantization.
Okay, you have
Yes, ma'am. 5 level. Yes, ma'am. Mid-trade.
mid trade. Yeah. This one is odd. This one is
Right,
even,
one is
and this one is for
optimal this quantization.
and compounder. Where the compounder is used?
Compander, ma'am. Okay, compander is used for this is non-uniform sampling actually. The upper two is for uniform sampling, and last two are for non-uniform quantization.
No.
Non-uniform
The
quantization.
compounder is utilized where, like, yeah. I agree. This is non-uniform quantization.
Yes, ma'am. Then where it is used, ma'am, it is used where, yes, ma'am, where the
Hmm.
large amplitude signal with large frequency, they have lesser chance of occurring. We don't need very refinement while quantizing them. But for those signals which are regularly occurring for a smaller frequency, there we expand their range. So this is companding.
Yeah. That was I was asking. So yes, this is non-uniform. Uniform or non-uniform, just name, and this is uniform. And you have mid-thread quantizer.
Where we
Quantization,
don't want too much refinement, there we go for non-uniform. Where we don't even want same rate of quantization for everything.
yeah. So quantization is nothing but a approximation, we can say, because we have
Estimate set of values.
to
Estimate set of
a
values.
specific set of values so that we can easily encode it. And the delta step size is V max minus V min divided by 2 power L, 2 power n, I
What is
think,
it?
bits. What is the
Okay,
formula
ma'am.
for delta step size? This one.
Ma'am, I don't think that told us
Okay.
full form of
Yeah,
delta. Once.
bits. Number of bits.
Uh,
Is it
number
correct?
of level. Yes, ma'am. It may be correct because two times. Yes, ma'am. Looks like it is correct.
Yeah.
Yes,
Because
ma'am. It's
this
correct.
2 power n is number of levels.
Yes, ma'am. Yes, ma'am.
Hmm. And noise power is what? Ideal noise power? Del square by 12.
Yes, ma'am. Yes, ma'am.
So these are the things which you need to remember. And I think fine. And I think beyond this, nothing will be asked in the exams. So, okay. So, the third question is, consider a superheterodyne receiver with a broadcast frequency FC and intermediate frequency FIF 500 Hertz. The corresponding image frequency is given as. So, yeah, please solve. So, we have FC is equals to 1 kilohertz, FIF is equals to 500 hertz, and image frequency we have image frequency formula is fc plus 2if.
Ma'am, two kilohertz. 2 kilohertz. Answer will be 2 kilohertz.
Okay, that's all. 2if is 1 kilohertz plus 2 into 500, then 1 plus 1, 2 kilohertz. Nice, very nice. So we actually have input as Let's see superheterodyne receiver in a brief so that you can also remember what is that, sir. So superheterodyne. So superheterodyne and heterodyne are same, but just the frequency, like F1 should be greater than F1 plus the 2 I.
Mixing
Mm,
mixing frequency is different, ma'am. F1 plus F2 in case of superheterodyne, F1 minus F2 in case of
F1 plus F in the superheterodyne and F1 minus F in a,
heterodyne.
yeah, yeah, yeah.
The outcome is actually same because when we multiply them, then we are getting this
Yeah,
centered around
yeah.
F2 and band pass filter.
Mixing frequency for heterodyne dyne, mixing frequency for superheterodyne. Okay. So these are the things, and you usually have this mixer cos. What is the frequency? Question
F1 plus F2, ma'am, or F1 minus F2,
or input is
anything. Input is in F1. This input message frequency sent. Yes, ma'am.
this is the IF mixer, and at the end, what are the blocks? Tell me.
Ma'am, amplifier,
This
then
one is, yeah,
demodulation.
yeah, yeah. So I was telling you now the difference between frequency super heterodyne and amplitude super heterodyne. So what you have here, since the output is in the terms of amplitude, so you will have the power amplifier in terms of power amplitude amplifier. Okay.
Okay, ma'am.
Otherwise, it will be simple frequency amplifier because we want amplitude amplifier. So power amplitude amplifier.
Ma'am, why we go for this amplification here?
Because here IF mixer deteriorates deteriorates sorry the amplitude, na, this amplitude and frequency varies differently.
Okay,
So
ma'am.
though the frequency or high actually adding and then the amplitude deteriorates significantly.
Okay, ma'am.
So power amplitude amplifier, and then what is the next?
Ma'am, then there is filter and demodulation stage.
Yes. So we'll require filter and finally demodulation to get the actual message because it is a receiver.
Ma'am, what is use of this filtering section here after amplification?
Yeah, because after amplitude you want what levels you require, right? So suppose you require this pitch. So you filter accordingly according to this use, purpose or use.
Okay, ma'am.
So these are not two main blocks of this. The main blocks is IF mixer, demodulation, because this is a receiver, so you require demodulation at the end. And demodulation also in the form of low pass filter. Receiver. You have IF frequency as F1 plus 2 IF.
No, ma'am, this is image
Yeah, yeah,
frequency.
yeah.
IF
Sorry.
is simply
IF is
F2.
F1 plus F2. Sorry. Image.
No, ma'am, IF is simply F2. IF will be simply F2.
Yeah,
That
yeah.
is
This one.
local
Sorry. And
oscillator
that
frequency.
that
Yes,
too is a 450. What is that frequency?
455 hertz in case of AM.
No. And this is
455
yeah. And for the frequency
kilohertz,
modulation,
ma'am.
kilohertz only. For the frequency modulation, you'll have a different IF frequency according to the spectrum range.
Yes,
Because
yes,
logically, if you see, you have 550 kilohertz to 1600 kilohertz, I think.
yes, ma'am. 540 to 1600
Uh,
kilohertz.
then this one is AM spectra. So we have to take in between this lesser than this one. Yeah, we have to take lesser than this one so that at the end we don't have any issue with demodulation as well. So image frequency is FC plus 2IF, FIF, and FIF is standardized is 455 kilohertz. And what is the frequency name for FC minus 2IF? FIF?
Don't know, ma'am. Sir didn't teach this.
Okay, okay. So this is also sometimes called at image frequency. When you have input as F1 F1 greater than F2, I think. Sorry, F1 less than F2. You
Okay.
visualize it using F1 minus F2 less than F2. You visualize it will be some homework for you. Okay. So this is all about super heterodyne receiver and the frequency and all. So we'll see the next question, which is a question number 4. So, 18 voice signals are sampled uniformly and 10 time division multiplexed. The sampling operation uses flat top samples with 3 microseconds duration. The multiplexing operation included provision for synchronization by adding an extra pulse of significant amplitude and also 3 microsecond duration. The highest frequency component of each voice signal is 4 kilohertz. Assuming a sampling at the Nyquist rate, calculate the approximate silence time between the successive pulse of the multiplex signal. Yeah. Kushit, have you seen this question before?
Yes, ma'am. Yes, ma'am. I'm working on it.
Okay.
It's actually quite simple, ma'am. This
Yeah,
is
yeah, yeah.
18 signal and one is for extra pulse of frequency.
So Fs is equals to 2 into Fm, and this Fm is the highest frequency present in the signal. Now, this now Fs will be 2 into now Fs will be 2 into Fm. And what is Fm? Fm is 4 kilohertz. This is 8 kilohertz. And then what is required? Calculate the approximate silence time between the successive pulse. uh, 18 voice pulses है तो uh, you also require one synchronization pulse, right? So 18
Yes,
plus
ma'am. Yes,
1,
yes.
it is 19 pulses. And okay, so let's calculate TS is equals to 1 by 8,
Ma'am, it will be D. Answer will be D, 3.58 microseconds.
3.58. Okay, can you tell the logic? Like what is.
Yes, ma'am. Ma'am, first draw one line. First draw one line in this time domain.
Yeah, yeah.
This is of duration Ts, which is
TS,
equal
which
to
is
1 by Fs sample.
125.
Yes, ma'am. 125. Yes, ma'am. Right, ma'am. Now, simply draw two, three pulses here for reference.
Yeah, yeah.
So each of these pulses are of three microsecond duration, and there are
Mm-hmm.
total 19 such pulses. So we will subtract this from Ts minus 3 times 19, and then we will divide it by the number of pulses to get this silence period between each pulse.
Wait, wait, wait. So this is 3 microseconds. Then 19 total you have,
Yes, ma'am.
right?
Yes, ma'am.
One is synchronization pulse.
Ma'am, total number of these silence period will be equal to 125 microsecond minus 3 into 19.
Yeah, yeah.
3 into
Mm-hmm.
19. And
So,
then we will divide it by the number of pulses, that is 19 again, to get this interval between two successive pulses.
Okay, so this is one is the total number of pulses.
Yes, ma'am. 125 minus 3 into 19 is total number of silence period in this one TS.
This is in the seconds, right? Okay.
Yes, ma'am.
Microseconds or what? Second microseconds.
Microsecond of, yes, ma'am.
Uh-huh. Total number of silence periods.
Period in TS duration, or 125 microsecond में how many?
Sampling duration. Okay.
Now
So
we divide it by the number of pulses to get between successive pulses.
calculate the approximate between. Okay, okay, between. Then we have to divide by 19, right?
Yes, ma'am.
Minus 3 into 19. What is the answer? I have to just check it once. Just wait for 5 minutes. Like you have told that this is one is a 3.58. This is actually coming 3.58.
Yes, ma'am. 3.57 and something after rounding of 3.58. Yes, ma'am.
Calculator. So this was given in the TDM session, right? Section
Yes, ma'am.
25. So yeah, question is very correct, and answer is 3.58 microseconds. Why this is? This is all about, this one is a time domain. We'll have the pulses here for the duration of 3 microseconds, and since you have 18 voice pulses, and one is for the synchronization pulse. This was I knew earlier also, but yeah, I was confused between this total number of silence periods, but it will be calculated using this TS minus 3 into the time duration of each pulse into number of pulses, using the synchronization, including the synchronization pulses, and how we will calculate the approximate silence time between the successive pulses. So it will again be divided by number of total number of pulses. So here silence time between successive number of pulses. Okay. So yeah, this is a question number 4, and now yeah, quantization is used to map a continuous time signal to discrete time signal, a continuous time aperiodic signal to a power signal, samples of a continuous time signal to a discrete set of values, and a random continuous time signal to a deterministic discrete time signals. This type of question can be asked in IES, I think IES.
Yes, ma'am. C.
Hello, Khurshid?
Yes, ma'am. C.
Samples of a continuous time signal to a discrete set of values. So you C, answer is C. Yes, correct. The answer is C. Why you are not thinking about aperiodic periodic here?
Aperiodic and periodic, ma'am. Quantization we simply do it. Here we come from analog domain to digital domain, and there is. I don't think there is something to look for this aperiodic and
Yeah,
periodic.
actually the question, the option number A, continuous time signal to discrete time signal, is not there.
Yes,
Because see, we'll see one by one options, because continuous time signal and discrete time signals are different only in time domain. So we are not
yes,
doing
ma'am.
that. Okay,
And
okay.
actually, discrete samples they can have an infinite number of values, but
Yeah,
after quantization they get to acquire only few set of
finite
values.
value. Yes, yes, yes. Nice
Yes, ma'am.
observation.
Finite. Yes,
Mhm.
ma'am.
So yeah, this one is wrong. And the second one is a continuous time aperiodic signal to a power signal. Like we are not only bounding it to aperiodic signal, and aperiodic signal can never be converted to power signal. It's very true. Because power signal is only for periodic, and we never saw here anywhere. So second option is also wrong. Now the third is samples of a continuous time signal to a discrete set of values. Yes, we are providing the approximation using levels and step size. Step size. So sometimes we have delta by 2 as maximum quantization error. error. So we are doing this. And the fourth option is a random continuous time signal to a deterministic discrete time signal. So this one is also doesn't make sense because we are not doing this one because Ramashri. Yeah. Hi Ramashri.
Hi, madam.
Yeah, you are joined little late. Can I know the reason?
Actually, mm, my network issue, madam.
Network issue. Are you getting the notification like I'm switching the class time and all? Like
Seven to nine.
Kushi said that we are only getting a formal mail through which the people are not getting informed, I think. Because earlier classes I used to have somewhat three, four, five students. Now I don't have. So this is the like. And can I know your assignments evaluation till now? Like what is the percentage you are getting?
90 marks, 100 out of 100, madam.
Okay, nice, nice. Okay, so please make sure that you are getting full marks in the next four or three assignments, so that you can
Okay.
easily pass the exam. And in fact, if you pass the exam with a good thing, na, then you'll get the gold and gold, elite, and silver certificate. Kushit, have you ever done any NPTEL course earlier?
No, ma'am. This one is my first
Which
time.
one?
This one, communication system.
Digital.
No, ma'am. This one I'm doing right now is my first NPTEL course.
Okay, okay, okay. So those who
Yes,
top the exam now, their name will be
yes,
there in the NPTEL website.
yes. It's good, ma'am.
Yeah. So the last option will be also wrong. Then we'll resume. So again, theoretical question. In delta modulation, the distortion that occurs when the signal rises or falls rapidly in comparison to the constructed signal is termed as
Slope overload distortion.
salt and
Slope overload, ma'am. Slope overload distortion.
what she's saying slope overload, no? Hmm. I couldn't hear. Yeah, why this is slope overload? What was the condition for slope overload? The condition was there, na?
Yes, ma'am. Delta is too small here, so it is not able to track.
No, no, graphically how we can solve?
Okay. Yes, ma'am.
The
Ma'am, first draw one.
no,
Draw
no, no,
something, ma'am,
no.
with large.
One mathematical expression was there, na? Delta less than TS or delta by TS was that what was there? That
Okay, let me check.
slope overload was slope is greater than delta by TS. Yeah,
No, ma'am.
this.
It was taught us graphically only in the lectures.
No, no, no. This slope is whatever this slope is that what is this slope? This is T delta. This is TS. Slope is what? Delta by TS, right?
Yes, ma'am.
And it should be greater than or very greater than FS. FS or what? Some expression was there. I'm missing.
Ma'am, what is
Slope.
this FS here? What is this FS and TS are same now?
Same, na, yeah, yeah. Some was there. FM by TS or somewhat. 1 by FM. Loop overload.
Modulation.
So delta by TS was greater than I have
Yes,
read
ma'am.
this.
Delta by TS greater than equal to maximum of the slope of masses signal.
Yes, yes, yes. That's why I was missing. Yeah. So,
Yes, ma'am. This is in textbook Simon Hacking and Michael Moore.
so This one should be max slope of FM. It should be there.
Ma'am, this one. Ma'am, just 1 second.
Uh,
I'm showing something.
it's not clear question. Okay, dm by
One
dt.
second, ma'am.
Okay,
One
okay,
second, ma'am.
got it, got it. Dm by dt.
Okay. Right, ma'am.
Slope
So,
of mt. Yes, yes. Using this equations, you generally got many questions directly. So please don't remember, forget this. Maximum flows is d dt mt is this one. Slope over load distortion is slope over load distortion is delta by t should be greater than or equals to d by dt of mt, and so delta should be greater than or equals to ts or 1 by fs. So I remember this formula, I forget a little bit. Now we will analyze whether this is having or not. So the distortion that occurs when the signal rises or falls rapidly in comparison to reconstructed signal. So MT. So reconstruction is what? This one. Suppose this one is the reconstruction. This is the MT. And the
excuse me,
signal
ma'am.
rises of
Excuse me, ma'am.
rises.
Ma'am.
Yeah, yeah, yeah.
Ma'am, I think this equality symbol should be opposite. Delta should be less than this slope. Then only this will happen. Na? It will be not be able to track this signal.
So the answer will be what? Slope overload or what?
No, answer will be slope overload, ma'am.
Or
But this delta should be lesser than this slope of massive signal, I think.
Okay, the condition you are saying.
Yes, ma'am. Condition. This inequality should be opposite. Delta should be less than equal to this slope.
Okay, okay. Sorry. Slope overload. The slope overload is concerned with the slope of message signal. Okay, sorry. Yeah, yeah. It should be less. It should be less, yeah. Slope overload, how we can remember the slope of message signal. So what is happening here? When the signal rises or falls rapidly in comparison to reconstructed signal is termed as a slope overload. So here the message signal will fall more rapidly. So you will have step size very less. So you were saying the step size greater than the small you were saying, na Kushan?
Yes, ma'am. Yes,
Hmm.
ma'am.
So small, how much small? This much small. Okay. Hmm.
Yes, ma'am.
Okay.
When this step size is too large, then granular noise error
Yeah,
comes.
granular noise error. Yeah, we also write that. This is the slope overload. How will remember slope overload? So sometimes I get confused between slope overload or slope of this quantization. But no, slope of message signal is concerned here. So slope overload case, granular noise is delta greater than or equals to 1 by fs d by dt mt. And you will have the practical scene, then you will have no errors, and finally you can reconstruct the signal. Again, this one. Okay. The uniform quantizer with an even number of quantization levels is
it is
mid-rise.
education contest.
Mid-rise,
Mid-rise.
ma'am.
Yeah.
Mid.
So we earlier also discussed this one is for even, this one is for odd, and this one is delta quantizer and DPCM quantizer. This is one is uniform. And can you tell me this one is uniform or non-uniform?
Uniform, ma'am.
Okay, nice. So yeah, next question. Consider a superheterodyne receiver with a broadcast frequency of FC. So here we call the FC frequency as broadcast frequency, you please remember. So an intermediate frequency FIF, the corresponding image frequency is given as,
Ma'am, FC plus 2 times FIF.
yes. So you please remember this one is Fc plus 2 times of Fif. You are getting where Fif is 455 kilohertz and Fc is generally, what is the Fc? 1000 kilohertz, in the range of 1000 for AM. And what can we calculate? We can calculate this one, 1000 plus 2 into 555. It will be more around 2 kilohertz image. So image frequency will lie around 2 kilohertz. Why I'm telling? Let us see. So see, you will have Fc as 1000 kilohertz. Sorry, this one is F. This is 1000 or 1 kilohertz we can say. And FIF is somewhat 0.5. If this is a 0, this 0.5 kilohertz. Then you are just making it to 2 kilohertz. So difference between this one is 1 kilohertz and this one is, difference is far less. Difference is 1 kilohertz. Difference is far less than difference of modulation. Modulation difference. So in this way, mixer and modulation differs. So if we take the case of modulation, then FM is converting to FC plus FM. Since FC is far greater than FM, so this conversion difference is high, which is the difference between these two. So since it was not recorded, so I have to tell again, so it's okay. Now the next question, GSM multi-frame has 26 frames with each frame comprising of 8 time slots. There are, so we have input given, let's solve, number of frames as 26 time slots with each frame comprising of time slot of each frame. Each frame is 8 and the bits, number of the bits per time slot, which is a bit rate per time slot. So bit rate is 156.25 bits per time slot, with each bit being 3.70 microseconds long. What is the approximate duration of GSM multi-frame? To find, how we'll calculate?
Simply we will multiply everything. 120.25 millisecond answer I'm getting, so it will be A.
120.25 milliseconds. Okay. So
Millisecond.
number of frames is there plus 8 into bit rate into each bit rate. So what is this? This is microseconds per bit. So we can, in fact, microseconds, and this is number of frames. So if you multiply all those stuffs, so this is microseconds per bit and time slot of each. So it will not have a unit. So 26 into 8, and which will get cancelled, and it is times slot of it is, I think it is time slot. And you can also check, always check using the units. So if you multiply all, sometimes if you need some tukkana, so you can try with the units. What is the unit you are getting? 8 time slot into 156.25 bits per time slot into 3.70 microseconds per bit. So what is that? Bits get cancelled. Time slot also get cancelled, and you are getting in the microseconds. So what is the answer question you are getting? Milliseconds.
120.25 millisecond. 120 millisecond.
So which is 120 milliseconds. I think the answer is 8. So yes, you can always check with the this units and all. Yeah. So last question we have come to. Consider a quantization step size of delta and an uniformly distributed quantization error. The power of the resulting quantization noise is
Yes, ma'am. Like you told, it is delta square by 12.
delta square by 12, right?
Yes, ma'am.
Why it is delta square by 12?
Ma'am, actually, can we discuss its derivation little bit briefly?
Yes,
Delta
yes.
square by 12, how we are getting.
Delta by 2, right?
Yes, ma'am.
This one
Ma'am,
is
this
here.
is probability distribution function or something, right?
Yeah. So how will you get? It was integration over this noise power. Not remembering the fact, but yeah, using this probability distribution integration and all, you'll get delta by 2, 12, delta square by 12, which is the ideal one. So this is ideal one. Sometimes in the question also you don't usually get actually delta square by 12. So yes, this one is the ideal one. I think we still have time. So we'll discuss for 10 more minutes. We'll complete by 8:30. Earlier sessions were not recorded. Only the questions and answers sessions is recorded. But fine, it's not an issue. But yeah, Ramashri, if you have any doubt in any session, just let me know. Ramashri, yeah.
present week అయితే డౌట్ ఉంది మేడం.
Present week, okay. So actually, in the present week, I'll deal in the next. I don't have material also. So present week, what was the topic? Can you tell me?
డిఫరెన్షియల్ DPCM quantization.
DPCM quantization. Okay. Other TA is also there. Kushit, you used to attend his class also, right?
Yes, ma'am. I have attended two,
Okay.
three classes.
So what he also teaches?
Ma'am, he actually goes directly to solving these questions.
Okay.
And many questions are actually repetitive, sort of. Some have actually typing error in the PPTs.
Okay. Okay. Mention. Quantization. So, Ramashi, I just wanted to tell you the quantization is somewhat is only the approximation to some sort of levels. Since DPCM deals with the message input and the difference between the message and the output, so you have some different type of quantization. So we'll see like how it is different. I think this one is for DPCM. So yeah, see, this one is a systematic diagram for the DPCM. So if you have input as MN and MPN, predictive nature of output, then you have this error, and then the quantization here we are using is this one. So other than other quantizer, you will have only the input as error. Since this one, if you see, will actually what we are doing. Suppose you have the message signal as this one. We're actually making it the approximation to some value. Suppose this value is something, so we are making it this one. Suppose this value is something, we are making it to this one. So we are actually approximating it. But the input was what? Here the empty was the input. But here the input you will have the error. So it will have somewhat different nature. Sir has not taught about DPCM quantizer. Question?
Ma'am, DPCM quantizer. There was this schematic of DPCM, sir taught us. No, that exact filter, how we are doing it, that's the thing.
The exact filter.
Yeah.
Okay, Ramashri, I'll let you know in the next class.
Okay, ma'am. Thank you.
Yeah, I'll let you know in the next class by going through the some books and all, because I also don't remember. But one thing I'll just tell you, that the this naturally occurring signals such as videos and audios have very high correlation, which is increases the redundancy, and in this way we can have DPCM because it reduces the redundancy by using the predictive nature of the output. So here it is utilized, and I told you the difference between modulation and mixer, which was required. And this week was very easy, so I didn't cover much to Kushid also, and he was actually revising all the stuffs which he has gone through. So okay, then I think it's okay. And if you have any doubt in any question, you can mail me in my email ID. And one thing I'll just suggest you, like since we are bounded to take the class for 2 hours, or somewhat it can converge to 1.5 or 1.2 hour. So if you want anything extra to learn, then please let me know. And one more thing, that for the exams, I'll just cover many questions related to that, so that you'll not have any problem in the exams. So okay, with these words, I'll take your leave.
Okay.
Okay, ma'am.
Thank you very much.
Okay, thank you so much for joining.